Hi everyone, welcome to MCTV Training Class 15. Today we will discuss an advanced control strategy in motion systems, the parallel servo loop, also known as feed-forward plus feedback parallel control. This architecture is designed to achieve high performance, reliability, and safety by combining open-loop prediction with closed-loop correction. It integrates the strengths of feed-forward control, which anticipates known disturbances, and feedback control, which correct unknown errors. Additionally, multiple feedback paths ensure verification and calibration, significantly improving dynamic response, steady-state accuracy, and system robustness. This approach is especially valuable in high-speed, high-precision applications where traditional feedback-only systems may fall short. Let's explore how this structure works and why it is so effective. Here is the structural diagram of the parallel servo loop. The target command R is simultaneously sent to both the feed-forward controller and the feedback controller. The feed-forward controller computes a predictive control force based on the command, while the feedback controller, often a PID, generates a corrective force based on the error between the command and the actual output. These two forces are summed at the summation point and then applied to the controlled object, such as a motor or mechanical system. The system output Y is measured and fed back for comparison. This parallel arrangement allows the system to respond quickly to commands while continuously correcting deviations, resulting in faster and more accurate tracking. The parallel servo loop consists of two main channels. First, the feed-forward channel performs open-loop predictive control. It calculates the required control force directly from the command, using models of velocity, acceleration, or friction. If the model is accurate, feed-forward can achieve zero phase lag. Second, the feedback channel performs closed-loop reactive control. It adjusts the output based on real-time error, providing robustness against model inaccuracies and external disturbances. Together, they complement each other. Feed-forward enhances speed, while feedback ensures accuracy and stability. Tuning a parallel servo loop requires careful steps. First, system parameters like inertia and damping must be accurately identified. Next, stabilize the feedback loop, usually the PID, before introducing feed-forward. Start feed-forward gains from zero and increase gradually while monitoring tracking error. Be aware that feed-forward can amplify noise in the command signal, so filtering may be needed. Also, in highly nonlinear systems, basic linear feed-forward may not suffice, and adaptive or nonlinear models might be necessary. Proper tuning ensures optimal performance without introducing instability. Now, let's turn to the series servo loop, also known as cascade control. In this structure, control loops are nested from the inside out, like Russian dolls. Typically, it includes an inner current torque loop, a middle velocity loop, and an outer position loop. Each inner loop's output becomes the command for the next outer loop. This layered approach is widely used in servo drives because it provides clear separation of control objectives and simplifies design and tuning. The series structure is mature, reliable, and effective in managing different types of disturbances at each level. The innermost loop is the current or torque loop. Its role is to control the motor's phase current to precisely regulate electromagnetic torque. With inputs from the velocity loop, it commands PWM voltage or current to the motor. Feedback comes from current sensors. This loop has the highest bandwidth, often between 500 Hz and 5000 Hz, allowing it to respond almost instantly to torque demands. Its high performance forms the foundation for the entire system's dynamic capability, ensuring quick rejection of electrical disturbances. The velocity loop controls the rotational speed of the motor. It takes a velocity command from the position loop and outputs a torque command to the current loop. Velocity feedback is typically obtained by differentiating position encoder signals, with a bandwidth ranging from 50 Hz to 500 Hz. This loop is slower than the current loop but faster than the position loop. It plays a key role in suppressing load torque variations and maintaining stable speed, preventing disturbances from quickly affecting positional accuracy. The series structure is designed with a key principle. Each inner loop must respond much faster than its outer loop, typically 3 to 10 times faster. This creates a decoupling effect, allowing outer loops to treat inner loops as ideal, fast-acting units. For example, the position loop designer can assume the velocity loop tracks perfectly, simplifying control design. Disturbances are suppressed step by step. The current loop handles electrical noise. The velocity loop manages torque changes, and the position loop focuses on final positioning accuracy. This hierarchical suppression makes the system robust and manageable. In summary, the series servo loop uses nested feedback loops to handle disturbances layer by layer, offering simplicity and reliability. The parallel servo loop combines feed-forward and feedback in parallel to enhance dynamic response and accuracy. While series control is mature and widely used, parallel control offers superior tracking performance when models are well-known. The choice depends on application requirements: series for robustness and simplicity, parallel for high-speed precision where feed-forward can be effectively applied. Both represent powerful tools in modern motion control. This is the end of today's training class. Thank you for your attention.